Good morning. This is your Stats Sensei, Mr. Spensey, and this is an exit ticket on the paired t-test. So, a sociologist was investigating the ages of grandparents of high school students. The sociologist collected data on the ages and years of the students' maternal grandparents by taking a random sample of 10 high school students out of 1,163. So, we have 10 students. So, this is our data. And um, this right here appears to be our population. Enter the data in L1, L2, and L3 of your calculator and complete the table below. Well, so if I went ahead and entered that data, and by the way, the reason this is paired data, remember paired data has to be tested twice, is we have 10 high school students, 1, 2, A through J, and we got the grandmother and grandfather's age for each one. So basically, the student was tested twice as to the age of their grandparents. And because the student was tested twice, that makes it paired. To be paired, something needs to be tested twice. Okay. So I input the data into L1 and L2, and I could subtract and go 75 minus 74 to get that information, or I can just go up to blue button 1, which is L1, minus blue button 2, which is L2, and it populates the differences for me, and I wrote them down in the table right here. Okay? All right, so we have all the data in the table. We have all the differences because we're going to be interested in the differences. All right, and we always want to run a paired t-test when possible because you control for outside differences when you use pairing. So it's a very powerful test, but it's not always available to us. So once it's a test at an alpha equal 0.05, does it appear that the grandmother is younger than the grandfather? Okay, so that means here's what we're looking for. Grandmother and father. That means the grandmother's age is less than the grandfather's age. Grandmother's age is less than grandfather. So that's what we're looking for. All right. So our formula. Well, our formula, once again, and I've said this before in the prior video, looks very much like the t-distribution. X bar minus mu s divided by square root of n. The only thing is we're working on the differences. So the average of these differences, because we took a difference here, difference just means subtract. So the average of these differences. All right. And then we have, so it's exactly the same, except we put the differences, the difference of the sample means, the difference of the population mean, and the difference of the standard deviation. Now, please remember, N is the number of pairs. All right. N is the number of pairs. And in this case, we have 10 pairs. We're not going to say that we have 20 data points or 30 data points. We have 10 pairs. So the number of pairs is 10. Well, I'm going to go ahead and now that I have that information in a calculator, I'm going to go stat calc, one variable statistics. And the list I'm interested in is not L1, but it's L3. So blue button 3. And it turns out my sample mean is negative 1.3. And really, this is going to be years. And a standard deviation of 5.7551. And as we said before, we have a sample size of 10. Now, what's going to be interesting is 0. Why? The assumption is that there is no difference in the age because we're running a hypothesis test. The assumption of equal means there'd be no difference in age. This will always be the case for paired data in our course. Okay, in our course, that'll always be the case. So we're going to run a one sampled paired t-test, and we need to see this written down. You don't have to say that it's the one sample paired t-test for means. It's really the one sample paired t-test for the difference in means, but we're going to just stick with the one sample paired t-test. All right, we're going to draw this thing out. And please remember, when you draw it out, we need to be centered on the mean. So we're going to be centered on 0. All right. So our mean is 0 right here. And we have an X bar of negative 1.3, and that's below that. And we also said that we wanted a grandmother younger than grandfather. That's what we were testing. So that's going to be the the way that we're shading, and that's going to be the way that we run our test. All right, so when we go to plug in, which is easy enough to do, we have negative 1.3 plugged in for X bar. The zero is plugged in for the mean of the difference, and for the standard deviation is 5.7551 divided by the square root of 10. Sometimes people like to be tricky, and because in math you don't really need zero, sometimes you'll see answer choices that look like this: negative 1.3 over 5.7551 divided by the square root of 10. Normally, we're going to write it like this to be more transparent, but sometimes you'll see it like this because they go, hey, we really don't need that zero. All right. Um, when we want to write our hypothesis, well, the assumption is it's equal to zero, so that's really easy. The ho is MD is less than or equal to zero. The ha, we said grandmother needs to be younger than grandfather. And if you're not sure, pick a grandmother's age that's younger than a grandfather's age, and that's less than. And so mu D is less than zero. All right. Please remember, this will always be zero. This will always be zero. You need to include the D's. And for any hypothesis test in this course, the ho will always be equal. So the one thing that changes from test to test is this inequality right there, whether it's a less than, greater than, or not equal to. And you'll need to read the problem to get that. All right, let's go ahead and run this test. So we're going to go stat test, and it's going to run just like a regular old t-test, stat test, t-test. Press enter. Our mean is zero. Oh, by the way, make sure data, because our data is all listed in L3. Our mean is zero. Our data list that we care about, let's go back to stat edit, is an L3. So we're going to have to change that L1 to an L3. We do that by pressing blue button 3. And we wanted a less than. We're going to calculate. And the probability of t is less than negative 7.143 is a pretty large p-value of 0.2465. And they gave us an alpha of 0.05. So 0.2465 is definitely greater than 0.05. So we're going to fail to reject the null. All right. There doesn't appear to be, based on our data, there doesn't appear to be a difference in grandparents' ages, or we can't say that there is because our p-value is too large to reject the ho. Okay. The confidence interval. Well, we're going to create a 97% confidence interval for the difference in ages, grandmother minus grandfather. And as you've noticed, this is almost exactly the same as what we used for a regular t-distribution, which was x bar plus or minus t star s divided by the square root of n. The big difference here is, once again, we're talking about the differences because we're talking about this column where we subtracted. All right. So we don't even know what the ages are. We just know that our differences are. That's all we care about. So the average of the sample differences goes here. The sample standard deviation of the differences go here. And n is the number of pairs. T star, we're going to calculate just like we did before. We have to be careful about that, though. There is a little bit of trick to it. Stat test, second vars, inverse t. And we wanted a 97% interval. So our area is going to be 1 minus 0.97, close parenthesis, divided by 2. Once again, this is exactly the way we worked before. The difference is we're not looking at 20 data points or 30 data points. We're only looking at the number of differences, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 differences. So our degrees of freedom are going to be 10 minus 1, or 9. All right. When we do that, we get a T star of 2.5738. All right. We now have all of our information, and I should go ahead and show you once again stat calc, 1 var stat. My data list is an L3, and there's my X bar and my sample standard deviation. and I have those recorded right here. Degrees of freedom, please don't forget, this is based on the formula n minus 1, where n is the number of pairs. So, all right, so in this case, number of pairs, or you could have just written 9 here, but that's where that all comes from. Now that we have that, we can go ahead and plug in. So our sample mean goes in for X bar. T star is right here, just copy straight down. Our sample standard deviation goes here, and our sample size is 10. All right, when we go to draw this, please remember we're always centered on X bar because this is a confidence interval. Hypothesis tests are centered on the population mean. So they're always centered on 0 for this. But this will be centered on negative 1.3. That'll be our X bar. And then we'll be looking for that lower value and that upper value. All right. So when we do this, we're running a one sample paired T interval. And the important part is that you tell us that it's a one sample paired T interval. All right. So let's go ahead and run this test. Stat test, drop down to number 8, T interval, just like we'd be running a regular T interval. Data, the only difference is we care about our differences, which we said were in column L3. So blue 3, if that's not showing up. And we need to make sure that we have a confidence level of 0.95. When we do that, we get a lower bound of negative 5.417 and an upper bound of 2.817. That test. Oh, it's supposed to be a 97% confidence interval. Sorry about that. T interval, 0.97. There we go. So negative 5.984 to 3.38. So what this tells me and what this means in real terms is because we went grandmother minus grandfather, the grandmother could be as much as 5.9 years younger to as much as 3.38. And that's on average. That's not for any one grandmother. One grandmother might be 30 years younger or 30 years older. But on average, we expect the average for grandmother to be no more than 5.9 years younger and not more than 3.38 years older. We don't know where in that range it is. And because zero is contained in the range, we can't say that there's a difference in ages. All righty, I appreciate you watching and look forward to seeing you on the next one. Thank you.